Alright, we're actually going to start this chapter 5 off in section 2. And we're going to start with a couple of theorems that were kind of like that day that we folded my face when I was on a dollar bill. So these next two theorems you're going to see here that are in your notes are pretty much corresponding directly to what we did that day we folded my face, except for it's not starting off with an isosceles triangle. So theorem 5-2 here, read it with me. It says, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. I want you to think about what a few of these key vocab words are, like perpendicular. We've had that before. Remember, it's when two lines intersect at a right angle. What does bisector mean? Bisector means it's cutting a line segment into two congruent parts. So here I have a line PM here, and it is dividing AB into two congruent parts, and it's meeting at a right angle. So what does it say then? It says then it is equidistant from the endpoints of the segment. It's talking about a point. In this case, our point is P, is the same distance away from A as it is from B. That's what that word equidistant means, equal distances. So if P is on this line and it's a perpendicular bisector, the line is a perpendicular bisector of some other line segment, then P must be the same distance away from the end of the line at point A as it is from point B. And it doesn't matter where I put that point. I could draw a point right here. Marker's a little off. Let's see. There we go. So I could put that blue dot right there a little bit lower, and I still know that it's the same distance away from A as it is B. Now, if I call this, say, point Z, that doesn't mean that ZA is equal to ZB. I'm sorry, ZA is equal to ZB. It doesn't mean that ZA is equal to PA. Obviously, PA is going to be a little bit larger, but Z is the same distance away from A as it is B. So let's see what we should be writing down here in our if section. It says if line PM is perpendicular to AB and MA equals MB, that means it's bisecting it. Line PM is bisecting AB. What can we say about PA and PB then? They must be equal lengths. So let's look at the next theorem here. This is the converse of the perpendicular bisector. Remember what converse means. You have converse, inverse, contrapositive. Reverse them, negate them, and then do both. So converse means to reverse them, right? So the top one said that if you have P and it's on the perpendicular bisector, then PA equals PB. This one's going to be the converse, so you're going to reverse those statements, and you're going to start off with PA equaling PB. So now we're going to see we've got the isosceles triangle here. And so if PA equals PB, then P must lie on the perpendicular bisector. Now notice there's no perpendicular bisector drawn here, but what it's saying is if you were to draw the perpendicular bisector of AB, it would have to go through point P right there. So let's read the theorem. It says if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. It doesn't have to be an isosceles triangle drawn. I could just draw a point P out here in space and tell you it's the same distance away from A as it is B, and then you should know that it's going to lie on the perpendicular bisector of it. So as we fill out our if-thens here, if PA equals PB, what can we say then? We can say then line PM must be perpendicular to AB, and MA must equal MB. So, like I said, it's a lot like when we folded my face that day when we had the dollar bill with my face on it. Let's see how we can apply it to some problems though. It says, what is the length of AB? I want you to pause the video and see if you can get the equation set up and then worked out. Alright, so what we have, we know that because of this arc, not this arc mark, but this hash mark right here and this hash mark, that AD is equal to DC. So D is the midpoint of AC. Or you could say that BD is bisecting AC. not only is it bisecting it, but it's also meeting it at a right angle. So because of that, I know that any point I pick and put onto BD, like if I put a point right here, that this point is the same distance away from A as it is C. And it just so happens, since this is a triangle, I know that the vertex angle here, B, is the same distance away from A as it is C. So this, BC, must equal BA. So I can set it up as 4x must equal 6x minus 10. Subtract 6x from both sides, negative 2x must equal negative 10. And then dividing both sides by negative 2 gives you x equals 5. Is that our answer? No, that's not our answer, because the question didn't ask for the value of x, it asked for the value of AB. So don't forget to go back and substitute in 5, and 5 times 4 is 20. So AB is equal to 20. Alright, let's try out another one. It says, what is the length of QR? Pause the video and give this one a try. Alright, once again, we can say that QR must equal QP. Why does QR equal QP? Because it is on the perpendicular bisector of PR. We know that because this hash mark equals this. So PS equals SR. And QS is meeting it at a right angle. So since it's perpendicular and cutting it in half, I know any point on line SQ is the same distance away from the endpoints of this line. So since QR equals QP, I can substitute those values in. 5n minus 7 must equal 3n minus 1. And so solving for n, I get 2n is equal to 7. No, not 7. I'm doing my math wrong now. 2n is equal to 6. Add 7 to both sides. That's what happens when you try to do too much in your head. And n equals 3. So if n equals 3, what's the length of QR? Well, I'm going to get 15 minus 7, which equals 8. And if you want to, you can take this right here and make sure that you did it right. 3 times 3, and substitute into the other side. 3 times 3 is 9, and 9 minus 1 is also 8. So this side should equal this side right here, which it does. So this one should be on your notes as well. It says, suppose the director wants a t-shirt stand to be equal distant from the paddle boats and the spaceship chute. What are the possible locations? So here you have an amusement park, and we want to set up, let me draw a small picture here. Let's suppose, nothing exciting here, let's put a star in. Let's see. So there's a star. And you could put, let's suppose the star represented where your location for the t-shirt stand is. If you can only put up one t-shirt stand, if you set it up over here, well, the paddle boats and the rolling coaster, those people might get off their rides and walk over and buy a t-shirt. But the spaceship chute people, they may not walk all the way over there. It might be too far. So this guy, the director, can only afford one stand. He wants it to be equal distant from the paddle boats and the spaceship chute, which is right here. So what are the possible locations? So I want you to pause the video and see if you can figure that out. Alright, so if you think about it, let's draw the line segment PS right here. And this thing, every year I do this. It's never quite pretty look to it, but I just got to make it go at an angle. And see, my computer never wants me to draw this perfectly. But let's pretend like S is a little bit further up, so that works out. So I want to know all the possible locations that I could put this star so that is the same distance away from P and S. And so what that means is, based on the theorem we've learned today, it must be on the perpendicular bisector. So let's draw a perpendicular bisector to it. So if we were to measure it out and move this line, I know this line is perpendicular to PSC, so it's not just enough to be perpendicular. I want it to be going exactly halfway through. So let's suppose that was halfway through. Now, anywhere you put this t-shirt stand, let's suppose we put it right here. the distance walking from the spaceship chute to the t-shirt stand will equal the distance walking from the paddle boats to the t-shirt stand. Now I can make that distance a little bit longer if I move it further down the line, but it's still the same distance away from S as it is P. If I wanted to make it the shortest distance possible, then I'm going to put it, not move the background, but put this right where they intersect. Let's try to move that back. So that would be the shortest distance between P and S on that line in between them halfway through. But the question is just asking what are, if I want to make it equidistant, what are the possible locations? So there's more than one location possible, and it's going to be anywhere on that perpendicular bisector. Now let's look at part B here. It says, can you place the t-shirt stand so that it is equidistant from the paddle boats, the spaceship chute, and the rolling coaster? So pause the video, see if you can make it so that it's also equidistant from the rolling coaster. Alright, so here's what we're going to do for this one. I'm going to draw, I already know all the possible locations so it's equidistance from P and S. But now I want to add the rolling coaster to it. So let's draw a line segment between P and R. And then let's choose, I'll make this a different color. Let's draw the perpendicular bisector to this. We'll try to make this look perpendicular, and later this year we'll talk about construction so we can make it exactly perpendicular. There we go, again moving the background. So I can move this line up and down. It stays perpendicular, but I want it so that it bisects PR. And now notice anywhere on this red line, it's equidistant from R and P. So let's find that star. Where's the star? He's hiding behind the lines now. Well, come on out. Here we go. So anywhere on the blue line you're equidistant from P and S. Anywhere on the red line you're equidistant between P and R. So the intersection right there of the red and the blue line, the distance from S to the star, P to the star, and R to the star are all three the same. So this will maximize our sales to all the lazy people that don't want to walk very far to a t-shirt stand. Doesn't matter what ride they're on, they're going to be the same distance away from the t-shirt stand there. So that's just one small application. Hopefully an amusement park can afford more than one t-shirt stand because they make a lot of money at those stands. And so this is talking about the distance from a point to a line. You can pause the video and read all that if you want. I'm not going to read it to you. But I do want to bring up something I think that's helpful for my students, and that is, what do we mean by the distance from a line to a point? So if I were to draw a line right here, and you pick a point, let's make a point on here, we'll use a star again. And I asked you, how far away is the line from the star? And so you want to come up and measure that thing. Well, that's kind of hard to do because some students might come up and say, well, the distance from this point to the line, and they might measure it like this. But then another student might come up with their measuring tape and measure from here to here. Obviously, the student that measured it right here is going to get a longer length than right here. So we need to have a definition of what does it mean for a point to be a certain distance away from a line, and how do we measure it? And so basically what this is saying, summed up, is that if you're talking about the distance from a point to a line, that means you're drawing a line that is perpendicular. You're measuring the distance of a perpendicular line from that point to the line. So as you can see up right here, if I talk about the measure or the distance from A to line L right here, I'm talking about not this line segment or this one or this one. I'm talking about what is the distance of that line segment, the line that is perpendicular to line L and goes through the point A. Same thing for B right here. And so that's what we mean. We're talking about the distance from a point to a line. And that brings us to a couple theorems now. So the first one here says, if a point is on the bisector of an angle, then the point is equidistant from the sides of the angle. So if I say point S is on the bisector of angle PQR, then it must be the same distance away from PQ as it is from RQ. So as you're filling out your notes, let's make sure we get these down. QS bisects PQR. SP is perpendicular to QP. They do that so we know we're talking about the distance. It has to be perpendicular. And SR is perpendicular to QR. What can we say then? Well, we can say, let's do that SP is equal to SR. And then that brings us to our converse. It says if a point is in the interior, remember what converse means, it means to reverse them. So here we got point S, and we know it's equidistant from the sides. So if it's on the interior and it's equidistant from the sides, then the point is on the angle bisector. So pause the video, see if you can fill that out without seeing the rest. That means you're thinking about it. If you can fill it out, then I know you're not just copying the notes as you watch the video. You're actually thinking about it and working it through your head. So see if you can fill that out first and then hit play. We got SP is perpendicular to QP, SR is perpendicular to QR, and SP equals SR. That tells me S is equidistant from the sides. What can we say then? QS bisects angle PQR. So let's try out this problem. I want you to pause the video and see if you can work these problems out. Alright, so this says, if you're looking at the diagram, we know that this is perpendicular, and I know that line NR, or ray NR, is bisecting angle MNP. So that means that point R right here must be the same distance away from this side of the angle as it is from this side. So RM must equal RP. And so now I can set these equal. Now, some of you might have been able to just guess and say, you know, I don't know what to do, but I'm going to set these equal. And sometimes that's great for getting by on a quiz or a test or an SOL. But I think you'll enjoy the class more, and you'll get it right, get things right more often if you understand why you're setting them equal. Because then it's not just guesswork, you're knowing your geometry. So we get x equals 5. Did they ask us to solve for x? No, they said find the length of RM. So you got to substitute 5 back in. 5 times 7 is 35. So RM is 35. What is the length of FB? Pause the video and try that out. Once again, because CF is bisecting the large angle BCD and FB is perpendicular to CB and FD is perpendicular to CD, I know I can set them equal to each other. So once I set them equal to each other, and I know my reason why I'm setting equal to each other, the geometry part of the problem is done. The rest is just algebra 1 stuff, subtracting 4x from both sides, subtracting 3 from both sides, dividing by 2. So x equals 3. They asked for FB, substitute that in. 3 times 6 is 18, plus 3 is 21. And you can check this should be 21 as well. 4 times 3 is 12, plus 9 is 21. And so that takes us to your homework. So I want you to do the odd problems on the worksheet I have for you. And if you have any questions, just make sure you write those down. But I want to see all of those problems done, all the odd problems done. Okay? I'll post a link where you can turn that in on Google Classroom. And if you need to, rewind this video, back it up, whatever you call it nowadays, and watch some more there. All right. Thanks for watching, and good luck with your homework.